Hello everyone. Welcome to the EasyPower Thursday Technical Webinar Series. My name is Jim Chastain. I'm your host for today's session. And before we introduce our guest speaker for this much anticipated presentation, we'd like to run a couple poll questions, in part because people are still getting settled and in part because we'd like to have some feedback on the audience perception of the topic. So again, thank you for joining us today. And please, if you would, participate by responding to these questions. How often do you recommend conducting a power flow study on a facility? And I know opinions can vary widely, but if you would please kind of give us your opinion, we'd appreciate it. Just as a housekeeping note, all attendees of this webinar would receive an attendance certificate via email that people usually use to support their ECU requirements. And so you want to make sure as you sign on that you use your correct email address. So it looks like we have a quorum on this topic. Let me share the results. All right, looks like we have a fairly good distribution there. Then the next question is, do your clients have to pay a power factor demand charge or penalty as far as you know? And again, I'm really curious to see how the distribution on this one comes back. We live on the West Coast in an area that's very sensitive to issues with the utility connection. All right, looks like we have a quorum here. Here's how folks have weighed in. Okay, looks like we're talking to the right group. And then finally, are you considering power factor correction at this time or annually? We do appreciate everyone attending today. This presentation will be recorded and posted on the website, and you can view it as you would like to at any point in time. So here's how folks have weighed in on this one. Good. As it turns out, we pre-recorded Pablo's presentation. He's consented to join us online so he can answer questions as they come up. So I would encourage you to enter questions in the question box. We will have a Q&A session at the end of the presentation, but you're welcome to enter questions as we go along.
Hi, good morning, good evening, everyone. Welcome to this webinar by EasyPower. My name is Pablo De Jarmy. I am from Mexico. I work for the company ENCOS, and today we will be talking about reactive power compensation and choosing the right solution. Now, when talking about reactive power, the real word we should be talking about is power factor. Now, low power factor is one of the most easily identifiable power quality problems, and it is also, of course, one of the most common power quality problems found in every kind of industrial and commercial facility around the globe. Now, low power factor may have severe economic repercussions on your electricity bill. On every country, I think that is different. But yes, there's always a penalty for low power factor, and it's not just economic repercussions. You may also have very severe technical repercussions on your facility for low power factor. Now, there is a problem within a problem that when you make a correction in power factor and that solution is not adequate, I think the solution will generate more problems than it was intended to cure. Poor power factor correction is a very, very likely cause for other power quality issues that may impact you further on production, on your equipment, on your safety. So it's very important to mind the power factor solution. Now, before we talk about solutions for power factor, I think it's important to go back a little to college, maybe, and remind What is power factor? What are the technical terms behind power factor? When we talk about power, steady state power at least, on DC systems, I make this distinction because when we talk about transient steady or transient state on DC systems, they can get very, very complicated, but on steady state power, it's very straightforward. The power spent on the system is the product of the voltage times the current on any element of the system. So it's very easy to identify, right? Now, when we make this product of volts times amps, we get, of course, watts. Now, when we talk about AC systems, this is not always the case, and it tends to get a little more complicated. Now, to talk about vectors and to talk about the mathematics behind these equations is very well beyond the scope of this webinar. So we're gonna just take what we want. When we, in an AC system, when we multiply voltage times current, the magnitudes of which, we're gonna get something called apparent power, which is expressed in a different unit, which is the volt amp, VA, which, as you may have noticed, is the unit in which transformers are rated, and also emergency generators are rated in volt ampere. When we talk about apparent power, there's two components to it. One is the P, which is the active power, and the other one is the Q, which is the reactive power. On the P, we're going to have watts, and on the Q, we're going to have VAR. This is the unit that we're going to use, which is volt ampere reactive. Now, don't mind these equations here. They're just for the record. They're just going to stay there. But there is a very simple analogy which you may have seen 1,000 times to explain what power factor is. Now, the relationship between these three quantities is very, very important because apparent power is the full power that we're using on the system. And that power can be divided into active power and reactive power. And of course, the proportions of every single element can be quite different, and they will turn out into a very different system usage. Now, you may notice that there is an angle here called phi, the power angle, that is the relationship between P and S. Now, the analogy I was talking about is, of course, beer. This analogy is used a lot to explain how power works in AC systems. What you buy from the grid, from the utility, is the full power, the kVA. This is what you buy, what you get when you buy a transformer. Sorry about the line, it's not very straight, I know. But you can use that power in many different proportions. You can have a lot of active power, watts. You can have a little reactive power, VAR, or you can have it the other way. You can have very little active power and you can have a lot of reactive power, which is not a good scenario because of these reasons. Active power is the real power transmitted to loads, and it converts to mechanical power, heat, or light. Now, this power is converted in motors, lamps, and heaters, and it very much can be felt through speed, torque, temperature, light. And the reactive power, it produces no real work, but it's essential for electrical machines to function. Now, this power is used and produced in the magnetic circuits of power machines. Without reactive power, motors cannot turn. Without reactive power, transformers cannot transform because the magnetic circuit doesn't operate. And therefore, it relates to the foam in beer. It's not what you would normally want in a jug of beer, to have your glass full of foam. But without the foam, the beer doesn't really work. But you have to keep it to a minimum, right? What you really want to have, what you really want to get from your whole bottle of beer, which would be the apparent power, is the active power, which is the thing that you're going to drink. It's a very, very simple analogy, but it works to explain how these quantities interact with each other. Now, the power factor is the ratio of active power to total power, which means it's P, watts, remember, over VA. It's how much power you're using in active things, in useful things, heat, torque, speed, versus all the power that you are buying from the utility or that you're getting from your system's capacity. Now, there are many ways to write this relationship, which is they're basically all the same. And power factor varies between 0 and 1. The best power factor is 1, which means that all of the power you are using is getting converted to active power, which means useful power. The worst power factor is 0 because it means that from all the power you're buying, none of it is becoming useful work, right? Normal power factor in facilities ranges between 0.6, which is very, very low, and 0.9, which for an uncompensated load, it's quite normal. So if you have a power quality study, power quality meter, and you find a value that is laying between these two numbers, it's quite okay. If it's any lower, it should be a reason for concern and for immediate correction. Now, think of this as the whole line for power, which begins at the generation, which can be either sun, wind, coal, gas, whatever it is, and then it travels through the line, through the transmission network, then through your transformer, to your facility, and then it ends up in a motor. The motor will require, for it to function, active power, watts, and reactive energy, bars. Now, think of this as a wire carrying current. The more components in the current, it's necessarily true, the higher it becomes in magnitude. So, what happens when I have a higher current in a wire? I have overheating, I have a large voltage drop, I have transformer heating, I have system derating. So, what would be an ideal solution for this particular scenario, particular problem? I can replace the reactive energy flow between the generation and the network with reactive energy that is locally generated and fed to the motor. So the motor will never know where this energy comes from, if it comes from the grid, if it comes from a local source. But on the other end, this wire is carrying less current, sometimes significantly less current, and the same amount of reactive power is being delivered. So this line with less current will have less heating, less voltage drop, less losses, and then another number of important gains. So this very, very simple chart is what reactive power compensation is about. To generate reactive power as locally, as close to the load as possible. And at the very, very heart of reactive power compensation, we have capacitors, and they will come in many shapes and many sizes. So what's the reason for utilities to give you a penalty, a fine, for having a low or high power factor? I'm going to go a little back and just remind that power factor is how much of the total power is being used and converted to active power. Now, in this scenario, what the generator, the utility sees, what they can measure in this cable is that they are delivering some active energy and delivering some reactive energy. So they have a higher current, they have losses, right? So when you go to a locally generated reactive source, the utility will only deliver active energy. the current in their wires will be less. And again, it's another, it's many factors that contribute to this. But they say, hey, this client is relieving my energy, my power lines. I'm sorry. This client is being kind to the grid by locally generating reactive power, so I will not fine him, and maybe in some cases even give them a little compensation. At least that's how it works here in Mexico. When you have a power factor over 90, the utility gives you a little something for the favor, right? Now, when we have a low power factor, remember that it all comes to a higher current. But when low power factor is held in a facility, you will have transformer overload, higher temperature in cables, system-wide losses, large voltage drops, economical penalties, less available power for your money, and large installation size. These two are very, very important because I'm sorry for the line, but these two very directly relate to cost. If you have a facility that is running on low power factor, you will have to buy larger transformers, larger cables, larger breakers, and that all costs a lot of money. But if you have a facility running on a high power factor, then all of your equipment can be sized to a smaller size. I'm sorry, and it will be much cheaper. And trust me, buying capacitors is much cheaper than buying a transformer or buying a generator or buying even cable. Capacitors are very economical, and if you invest in capacitors and you invest in a high power factor, you will need to invest a lot less in transformers and cables and generators, which tend to be very expensive. So it's financially a very wise move. Now, when we talk about power factor correction, we can mainly talk about two kinds of solution: passive and active compensation. Passive compensation is the traditional solution which works on capacitors and reactors, and that's pretty much it. It works at any voltage level. You can use it in low voltage, medium voltage, even high voltage. Utilities tend to use a lot of capacitor banks for the stability of the network, for voltage and rise, and it's suitable for pretty much almost all applications, and it's a low loss solution, which means it doesn't cost more in the long run, right? Now, capacitor banks can be fixed or automatic, which means they can have specific capacity, which will work for the entire time, let's say 25, 50 kVAR, or automatic, which are comprised of several steps of fixed capacitor banks, and the bank will analyze the network and it will activate as many steps needed, right? So obviously, automatic banks are a little more expensive than fixed banks, but they do tend to work better. Now, when we have very polluted networks with harmonics, which is another major power quality problem, fixed capacitors don't tend to work very well. Automatic capacitors, they work fine most of the time. But when we have very polluted networks, and by pollution I mean high harmonic content, which comes from electronically controlled devices, PWM, motors, transformers, and pretty much any modern machinery which has a high harmonic content. Capacitors do not tend to work as well as in traditional systems, but nowadays traditional systems don't exist anymore because every facility has computers, has electronically controlled devices pretty much everywhere. Now, capacitors do not tend to respond well to high harmonic content because they can have internal overvoltage, internal overcurrent, which degrades the device and shortens the lifespan of capacitors, including many other electrical phenomena like overvoltage when connecting other capacitors, right? So a way to improve the performance of these capacitor banks is to add detune reactors, which control in a way the harmonic contents of the bank. Now, these capacitors working in series with detune reactors can be as well fixed. It's very rare to see a fixed standalone capacitor bank with detune reactors. They do exist, but they're not as common. They're, you will find them most likely being automatic units, large units like over 100, 150 kVAR. And the switching can be mechanical, which of course has advantages and disadvantages, or terrestrial control, which is all the frill in the market right now. Now, there are as well hybrid solutions that can contain fixed capacitors, mechanical switching, and terrestrial control switching all in one unit, and that's a very elegant, very nice solution. Now, when you're going to buy a bank, a capacitor bank that has detuned reactors, you may find that the detune factor is 5.7, it's 7, it's 14. So there are a lot of options to choose from, and the manufacturer will not always be clear as to where you can use or you can't use them. But that's what this webinar is for. So there are also harmonic filters, which are composed of capacitors with not detuned but tuned reactors, which are made on purpose to absorb a lot of harmonic content. Now, it's not always very common to see these, but they do exist. Now, on the other side, it's the active compensation, and these devices do not have as many capacitors, as many reactors as the passive solution, but they work on power electronics. Active compensation is a way of following the system voltage, the system current, and then immediately, or well, as fast as possible, reacting to any changes and trying to compensate. Now, the response time on the active compensation is very, very fast. It can be as 10 microseconds. Of course, this solution is more expensive. It's for the most demanding applications. You can install it wherever you want if you wish. But of course, you will get more for your money if you install it where it is intended to be installed. They also work on every voltage level, maybe not always directly, maybe they have to be installed through a step-up transformer, but that doesn't mean they don't work. And they do current balancing, which passive solutions typically do not do. On this side of the correction solution, we have active harmonic filters, which they copy the voltage and the current waveform on the system, and they produce an inverse wave that cancels out the harmonics. And the SVG, which is the static VAR generator, which doesn't filter harmonics, it just produces VAR. But it also balances those. So those solutions are very good, of course. They are much more expensive than a passive solution, but they do tend to work very well. It all depends on the application. Now, if we put all the solutions in a graph like this, on the blue side, there's low voltage. On the green side, it's medium voltage, high voltage. And we start with the vertical axis, which is money. It's just what you're willing to invest. And on the horizontal axis is the performance. And then you go up from the fixed capacitor bank, automatic capacitor banks. Then you can add the tune reactors. Then you can have the tune reactors with the terrestrial controlled switches. And for low voltage, SVGs and active harmonic filters are top of the line. When you're working with medium voltage and high voltage, you will find pretty much the same: the capacitor banks with reactors. And then we go to very advanced solutions like the SVC, the static var compensator, and the STATCOM, static synchronous compensator. These two are pretty much used by steel industry, which have very large melting furnaces. arc furnaces, which are very, very demanding on the electrical system, and utilities. You can install them, of course, anywhere, but where you will get the full benefits of the solution is at a a high performance installation, a very demanding installation. So we have a lot of options, and then we have to decide where to install the solution, right? We have low voltage, we have medium voltage, high voltage, and for every voltage level, there's a wide range of solutions. So, where to install the power factor correction solution? It's like real estate, location, and where can I install? I can install on the. This is a very large facility. This is a high voltage bus, 115 kV. I can install some capacitor banks here, of course. I can do it on the medium voltage bus, which is 34.5 kVs, or I can make correct power factor at the substation level and then compensate for all the loads, which would be number three, or I can install a capacitor in every single load at the plant. So which one is correct? And I would say neither. There is no straightforward correct solution for power factor correction. So it may seem a daunting task to select, well, should I install an active filter at number four? Should I install an SVG? And at number three, should I install a fixed capacitor bank at number two? Because when you start adding solutions and you start layering your facility, they do tend to interact with each other, sometimes in a good way, sometimes in a very bad way. So it's kind of hard to decide between all the many solutions and where to install them. So many questions arise for you as a facility manager on which is the correct solution for power factor correction. By the first question would be, well, how many kVAR, how much do I need to invest? Where will I place it, on the low voltage or the high voltage side? Now, when I'm buying either low voltage or medium voltage capacitor banks with reactors, which they are commonly called filters, but they are really not filters. Well, which frequency should I tune them to? 4.2, 3.8, 2.7? How can I know if a contractor is making the right decision for my facility? And when can I get the best bang for my buck? Because always investments must have some return. Um, and then you can invest a lot of money on a system that it will work on the high voltage side, but that will not really help the low voltage side or the other way around. So when making this question, it's not just about how many dollars you're going to spend per kVR, but you must consider the system performance. When you install the solution, will the harmonic distortion go up? Will it go down? Will there be a voltage rise? Do I have a harmonic problem in my facility right now before installing the solution? So there are many things to consider. Now, reliability is always to be considered as well, because if you install 100 capacitors in every machine in your facility, it's bound that one of them will fail, and then another and another and another. But if you install just one big capacitor at the utility connection, it's very much likely less to fail. So there are many sides to this problem, as you can see. Now, when we improve power factor, remember that one of the key points of low power factor was high losses, because we have high current, high heating. So, of course, when correcting power factor, we will have decreasing losses, but depending on the location of the capacitors or whatever solution you take, losses must be considered, because they can also impact on the on how much money the project will bring you back on the long run. Now, to assess this problem, this power factor correction problem, we have two fundamental tools. One is a nicely performed power quality study in your facility. You can have a portable analyzer or a permanent solution, a permanent metering solution. And with this information, we can design a solution using, of course, EasyPower. Now, I'm going to make a very brief EasyPower example on how different compensation techniques. Now, this is not going to encompass all the solutions because it's just too much, but I'm going to make a very brief example on the impact that these solutions bring to a system. So before I turn to EasyPower, I would like to thank you for your attention. After this example, we're going to have a 10 minutes question and answer session, of course. And if you need more info, feel free to write me to this is my email. I will try to reply as fast as possible. All right, now this is the one-line model of the example I was using previously. It's what remains of a big facility. They have a large transformer, 12 kVA. They have a 115 kVA connection to the utility. Then they go down to the 34.5. And then I just left one substation because this facility would have as many as 12 transformers, big one transformers. But I left just this one for the sake of this example. Now, this transformer holds three loads, 200 kilowatts each. The kVR requirement varies between the loads. They all have a very similar harmonic composition with its fifth harmonic, 7, 11, 13, and their respective percentage. And now I have various propositions for power factor correction. So let's say that I did a power quality study with a handheld analyzer on my facility, and then what I found was that I have these three loads as model as here. Now, when I run the model on the power flow model, I find that I need 392 kVARs in my at the top of the system, so the utility can see a unity power factor, right? Which would be ideal. So I can face this solution with a medium voltage capacitor bank, or by installing, let's say, a capacitor bank with a detuned reactor in the substation. I can tune it to 5.7, 7%, even 40% if I have a very high third-degree harmonic content, or I can use single capacitors on every load of the plant. I can use 100 capacitors if I want. So what would be the benefits and the disadvantages of each? Let's say that I choose this solution and I choose to compensate on every single load of the plant. So I add a capacitor, which is a 50 kVAR capacitor, and that's it. So what happens upstream? I still have a very large reactive power requirement, but how's the power factor? It's acceptable. It's up to 92, so it's all right. It's all right. But then the facility manager, he says, no, I want a unity power factor. You got to install something on the middle voltage side. Okay, so then I put this bank on the middle voltage side, and it's delivering 300 kVAR along with the banks downstream, right? So then I go up to the utility, and then I went a little on the capacitive side. I went a little overboard, but I think that would be okay. That would be acceptable, and I'm very, very close to unity. So the plant manager is very happy. But then I start having a lot of problems on the production line because machines get it stopped, lamps start blowing, and then the transformer is very hot. All my wires are very hot. And then I start having a lot of problems since I implemented this solution, which in theory works very well. But then I go and check what happens on the harmonic side of my facility, right? So I make a new measure, and then I find that I have an unusually high voltage distortion, total harmonic distortion for the voltage, for the current. And these capacitors, instead of lasting 10 years, are just lasting 6 months because they are absorbing too much harmonic current. So, how was I before the solution? Before implementing this solution, I was I was running a little bit on the hot side with the distortion, but it was acceptable. So I had no issues with my drives, I had no issues with the machines. But then a contractor came and they installed some capacitors, and then the distortion started going up and up and up. And then when the plant manager decided to activate this capacitor, the whole thing went to hell. And then we started having a lot of failures on the facility, right? So was this a good solution? No. Was it an economical solution? Yes, maybe. Was the power factor corrected? Yes. But then many other power quality problems began to arise, which will become much more expensive than what we had at the beginning. So, okay, that was not a good solution, right? So I'm here at the beginning, and then I need 382 kVRs. So then I decide to implement my solution at the substation level. And I'm going to do it with capacitors, but they're going to have detuned banks. So I'm going to go with the most common, let's say it's 7%. And this one provides 130 kVAR. So how are things looking up there? Well, they are much better. We should have a power factor over, let's say 92. Yes, of course, 92. And then it works reasonably well. And what happens on the harmonic side? Are we better than we used to be? Is this solution a good solution? I think it is, because without these capacitors, I have a higher, albeit slightly higher, distortion, right? On all my buses, 9, 8, 9, 6. And then I implement this solution, and then the distortion goes down in all of the buses while improving the power factor. So was this a better solution? Yes, it most definitely was. So we can try and choose from many solutions that are proposed by a contractor or by a manufacturer and see which one works best for my particular case, my particular facility, because they don't always react the same. You have to see how these solutions interact with your system. And this is why we use EasyPower as a wonderful tool. So these problems arise at the design stage and not at the later stage when they can be extremely costly and extremely complicated to eradicate. So again, this is a very simple example of how we can use the power flow model to assess the active power, reactive power, and power factor in all of the system, but also to check how all the components interact harmonically. For example, this is a capacitor bank that is tuned to a particular frequency, but if I start adding capacitors at the bottom, then I will have a system that is much, much complicated and prone to failure, because then I have a resonance very close to the 11th harmonic, which is a very popular harmonic, and this system is bound to have a lot of troubles. So before investing a lot of money on whatever solution, we can make a very simple design on EasyPower to check how it will work. So I think that's it for me now. I very much appreciate your time, your attention, and if you have any questions, please feel free to contact me. Have a very pleasant day. Goodbye.